Hi, I'm Shanawaz. This is the 8th lecture on metric spaces. We'll begin this lecture with the theorem. And it states that if we are given a metric space xt, then we have the following. The empty set and the whole space X itself are open sets in the XD in the metric space xt. That is, the empty set and the whole set X, they are the open sets. Now second part is the union of any arbitrary family of open sets is open. Arbitrary family of open sets in X are open X, and finally the intersection of any finite family of open sets is open. So we'll begin with part first. The empty set is open in the sense that there is no points in X of which the empty set is not neighborhood. In other words, as the empty set contains no points, the requirement that each point in empty set is this empty set is the center of an open ball container in it is automatically satisfied. The requirement that each point in this empty set, each point in this empty set is the center of an open ball contained in it is automatically satisfied. Contained in it is automatically satisfied. Now the whole set X is open since every open ball centered at any of its points is contained in X. the whole space X is open, and the reason being is that since every open ball centered at every open ball centered at any of its pointers centered at any of its pointers is contained in X. Now for the part second, let us consider an arbitrary family of open sets, and let G alpha, where this alpha belongs to lambda. Now this lambda is an arbitrary set. This is the indexed set. Now we have a family of open sets G alpha in X. Be an arbitrary family of open sets in X. Now we have to prove that the union of this family is open. Let us denote this union by H, i.e. H is union of G alphas, where these alphas belong to this lambda. Now we have to show H is open in X. Now there are two possibilities. If H is empty set, then by part 1 we are done. If H is empty, then by part 1 it is open. Now if H is not empty, so we assume that H is non-empty. Let us consider any point X in H. Let X belongs to H be any point. Now if X is in H, then this must lie in some G alpha, where this alpha is in lambda. Then this X belongs to G alpha for some alpha in lambda. Now G alpha being open, since G alpha is open, then by definition of open set there exists an R positive, where R is some real number, such that any open ball centered at X with radius R is contained in G alpha, and G alpha itself is contained in H. Since G alpha is open, there exists an R positive, a positive real number R, such that the open ball centered at X and radius R, this is contained in G alpha. because G alpha is open, and this G alpha is contained in H because H is union of these G alphas. So this implies that for each X in H there is an R positive such that the open ball centered at X and radius R that is contained in H. Thus for each X in H there exists an R positive such that SXR this is contained in H and H is contained in this is contained in some this contained in H. So consequently H is an open set. Consequently H is open. Now let us prove part third. Here we have to prove that intersection of any finite family of open sets in H in X is open in X. So let us consider a finite family of open sets. Let Gi, where this I varies from 1 to n. This I is an integer, positive integer, which varies between 1 and n. So this is a set of n elements where each element is an open set. Be a finite family of open sets in X. Now we have to show their intersection is an open set. So let us denote their intersection by G. Let G is equal to intersection of these Gi's, where this I runs from 1 to n. If G is empty set, now G is empty set. If G is empty set, then we are done. Suppose G is non-empty. And let X be an element in G. Now if this X is in G, then X must be in each Gi, where I runs from 1 to n. Then X belongs to Gi, where this for each I is equal to 1, 2 through n. Now since each Gi is open, then by definition, since each Gi is open, then for each Gi there exists positive real numbers Rj. There exist Rj, where j runs from 1 to n. such that each open ball centered at x and radius rj, this must belong to G Ri, I mean. This is Ri. This is Ri. Such that these open balls, they belong to Gi, where this I runs from 1 to n. Now what we are going to do, we will take minimum of these radii. Let r be the minimum of r1, r2 through rn. Then clearly r is positive real number because each ri is positive, and the open ball centered at x and radius r, this open ball must be a subset of each open set Gi. So this will be a subset of Gi for all I runners from 1 to n. Therefore SXR set therefore the ball SXR centered x satisfies the following condition. Therefore the ball SXR centered at x at x satisfies SXR. This is contained in the intersection. Since SXR is in each Gi, so this open ball will also belong to their intersection. So this must be contained in the intersection of these Gi's, which is called equal to G. This shows that G is open set, and this completes the proof. Now note that when we prove that union of arbitrary family of open sets is open, we take any arbitrary family, but this is not true when we take the intersections. For example, if we consider so this is not true for the intersection, i.e. the intersection of arbitrary family of open sets need not be open. The intersection of arbitrary family of open sets need not be open. To see why, let us consider let Sn, where Sn is the ball centered at the origin 0 with n with radius 1 over n. So let us take this open ball in the complex plan. So this is centered at C, and this n is a natural number, i.e. n is 1, 2, so on. Now this, by definition, each open ball is open, so each Sn is open set. Each Sn is open ball in the complex plan and hence this is the open ball in C. Now if we denote let C equal to intersection of all these Sn's, where this n is in N, so this Sn need not be open because this is nothing but this is the open balls of where n runs from 1 to infinity Sn, and this is a singleton set because S1 will be a ball centered at origin and with radius 1, and this is S1 because radius is 1, this is 1 unit. Now S2 will be a ball centered at the same point origin but with radius half, so this will be S2, this is half radius, and S3 will be, this is S2, this is S3, will be another ball centered at the origin and with radius S3. So if we go on like this, we'll end up with the singleton set, this which contains only 0. And note that this is not an open set because if we take any open ball centered at origin that contains infinitely many pointers other than the 0, so that open ball need not be a subset of this singleton set. So we see that arbitrary union of open balls is not arbitrary intersection of open balls need not be open. Clearly, which is not open, which is not open. Since there exists no open ball in the complex plan with center 0, that is contained in 0, so this is the reason. Next, we are going to define the derived set. So we have the following definition. Let X be a metric space and F a subset of X. Let Xt be a metric space and F a subset of X. A point X belongs to X This point is called limit point of f. A point x in x is called a limit point of f if each open ball with center x contains at least one point of f other than x. If each open ball centered at x contains at least one point of f different from x. Different from this small x. This is same as if that is if this open ball which is centered at x and say a radius r, where r is some arbitrary positive real number, so this open ball must contain a point of f other than x. So if we remove x from this set, so this set must have a non-empty intersection with f. So this intersection should be non-empty, must be non-empty. In that case, this x is said to be limit of this point f. So note that f may have infinitely many limit points, and a point in x which is not in f, that may also be a limit point of f. The set of all limit points of f is called the derived set of f. The set of all limit points of f is called the derived set of f, and is denoted by f prime. So by f prime we mean the set of all limit points of f in x. So let us do a couple of examples. So if we consider a subset f of real numbers, let f equal 1, 1 by 2, 1 by 3, so on. So this is a subset of real numbers. Then we claim that 0 is the only limit point of this set f. In other words, f prime, the derived set of f, is the singleton 0. Then 0 is the only limit point of f, that is f prime is the singleton 0. One can see over here, so if we take the interval 0 let us consider the interval 0 1 over here. So this is 0, this is 1. Now these points 1 by 2, 1 by 3, 1 by 4, so on. So these are the pointers which are in f. So as we approach to 0, the distance between these points becomes arbitrary small. So if we look over here, the pointers in the set f, so they may be arbitrary, they are arbitrary close. Now any open ball in real numbers is just an open interval in the real numbers. So if we consider any 2 points over here, any point over here, we may get an open interval whose length is arbitrarily small, which may not contain any point of f other than that point. But if we take the same interval over here, however small, like this always will contain, this interval always contain the points of f other than this 0. So this 0 is limit point of f. However, 0 does not belong to f, but 0 is limit point of f, i.e. 0 belongs to f prime. So by definition 0 is the only limit point of f, because if we take any other point of f, say 1 by 4, we may get some interval, some open ball over here settled at 1 by 4 which do not contain any point of f other than 1 by 4. So this is one example. For another example, let us consider the set. Let z be the set of integers. So this is the set of integers. Note that no integer is no real number is the limit point of set z of integers. So if RD be the metric space, R is the metric space, and Z be a subset of real numbers, so Z is obviously the subset of real numbers. So no real number can be a limit point of Z. Suppose if we take this point over here, so obviously if these are integers, say this is 1, this is 2, this is 3, this is 4, this is 0 over here, this is -1, so these are non-integers, i.e. they are decimals over here. So no real number can be a limit point of this set Z of integers. For example, if we consider this real number over here, so we can draw an open ball around this point over here which contain no point of Z. Even if I take an open ball around 3, say, so this open interval does not contain any point of the set Z of integers other than 3. So we conclude that Z has no limit points. Let Z be the set of integers, then Z has no has no limit points. So that have no limit points. In other words, Z prime is empty. Now if we consider the set Q of rational numbers, let Q be the set of rational numbers, then any real number Q then any real number R is the limit point of Q, then any real number is a limit point of Q is a limit point of Q. Suppose now here our metric space is R, and suppose these are the rational numbers. Since between any two real numbers there are infinitely many rationals, so if we take any real number, say this is the real number X, so I claim that this real number X is a limit point of Q. The reason being, if I take any open ball over here, over this, around this point X, however small, this interval always contain not just one but infinitely many points of Q other than this X, i.e. this interval contains infinitely many rationals other than this X. So in this case, we conclude that Q prime is the set R of real numbers. Similarly, Q complement, the set of irrational numbers. If Q complement be the set of irrational numbers, then Q complement prime is also R, i.e. the derived set of irrational numbers is the set of real numbers itself. I think this is it for today. Thank you so much.